So, today I want to give you all a little overview on the different types of resonance patterns that are possible. So, the first one is what we call an allylic lone pair. What this means is very simple. There is a lone pair, or multiple in this case, beside a double bond right here, right? So, how this resonance pattern works is, remember, we need to keep in mind a few rules. For atoms such as carbon, you cannot exceed the octet, so no expanded octet, right? And we also want to minimize formal charges on the molecule. And everything should, in the end, be satisfied with the complete octet. So that is what we're aiming for. Sometimes resonance structures cannot accomplish that, right? But that is sort of the main goal of resonance structures, or trying to find stability within a molecule. So let's look at how resonance would work here. There's a lone pair over here, and this is not ideal because we have a negative formal charge. What this is going to naturally do is this lone pair of electrons is going to come and form a double bond here, and this double bond is going to go become a lone pair on this carbon atom. So the reason this lone, remember, when you join resonance, it's usually involving two arrows, because if you're moving electrons from one place to another place, we need to do some redistributing in the molecule so that the octet rule is still being followed, right? So let's draw the new molecule now. These electrons have hopped on and made a double bond. So I'm going to make a double bond with oxygen. And now we have one less pair of electrons on the oxygen. However, because this double bond has gone and become a lone pair on this set of carbon, we have a more negative carbon. And the reason it's negative is because, remember, there is a invisible hydrogen here, or I'm just going to draw it. Doesn't really matter. Say, like right here, we have an invisible hydrogen. So now we have the formal charge on this becomes 1, 2, 3, 4, 5. And that's why we have a negative formal charge on that carbon. Now, which do you think is going to be more stable? Resonance structure A or B? Well, the more stable one is going to be A, and the reason is because we have a negative on a more electronegative atoms. More electronegative atoms have a better pull on electrons, which means they're happier handling that negative charge. Versus carbon, right? Carbon is less electronegative than oxygen. Hence, we would prefer compound A. Okay, now let's look at the second pattern, known as allylic carbocation. Allylic carbocation is basically when you have a positive charge on a carbon, and what this means is that that carbon is deficient in bonds. Okay, so how you want to interpret this carbocation is that it has two additional bonds to hydrogen, right? So it's actually not fulfilling the octet rule. So what is going to happen is this double bond is just going to go and hop on here instead. That's it. It's just going to hop on there. And now what we're going to end up with is something that looks like this, right? But one thing you have to remember is that this carbon has now lost a set of electrons. So this carbon is now going to become positive. If you're noticing a pattern here, it's that the charge is always conserved, right? The overall charge is always conserved. In resonance A over here, we had an overall charge of negative, and in B, we have an overall charge of negative. It just switched atoms. Same with these two, right? They're both positive. It's just switched on the location. Now, this is very important because if you find yourself drawing a resonance structure and you somehow seeing that the charges are not matching up, right? On resonance structure A, you have a charge, an overall charge of -2, and on resonance structure B, if you have an overall charge of +5, you know something has gone wrong because the overall charge is conserved. Now let's look at number 3, lone pair adjacent to a carbocation. So we have two lone pairs over here on this oxygen, and we have a positive carbocation here. Again, deficient in electrons. So what I'm going to do is I'm going to bump these electrons over here. And what's going to happen is we're going to basically just create a double bond. Now, what has happened here is we're not using two arrows, right? We have created this resonance structure only with one arrow. And that's because we're simply fulfilling the octet. What's happening here is now we have a positive charge on this oxygen instead of the carbon. Now, if I asked you which one of these structures is more stable, what would you tell me? What would be the more stable resonance structure? To assess the stability of a resonance structure or the major contributor, the first thing we look for is octet. Okay, so which one of these actually has a full octet? This carbon over here doesn't have a full octet because if it's a positive, that means it's missing one bond. So it only has one more bond to hydrogen, right? Over here, we actually have a complete octet. This atom over here, the carbon has a complete octet. It has 2, 4, 6 plus a little hydrogen, right? So that's 8 electrons. It's fulfilled, it's 8 electrons, it's fulfilled, it's 4 bonds. So this carbon now has a complete octet. This oxygen, even though it has a positive formal charge, is not ideal, still has a full octet. So this would be our major contributor. Okay. Let's look at this option over here. This is a pi bond between two atoms of differing electronegativity. This would be our fourth pattern. We have a pi bond here between carbon and oxygen, right? Those are our two different electronegativities. The electrons are going to be attracted towards the one with a higher electronegativity. So the electrons in this pi bond are naturally going to gravitate towards the oxygen. And notice here how there's only one arrow. There isn't two. So what we end up with is this. Now the formal charge on the oxygen becomes negative, the formal charge on the carbon becomes a positive, and together we're still seeing a conservation of charges, right? Plus, minus, they cancel out, we have a charge of 0. Which one is the more stable one? This one is clearly more stable because it has less formal charges, right? We don't want any formal charges like plus or minus. It's better to avoid them entirely, and if your molecule avoids them while having a full octet, we automatically know that is a major contributor. Finally, let's look at the last pattern, which is conjugated pi bonds in a ring. This is quite simple, really. This is a benzene ring, and the pi bonds just hop around. So this pi bond can go here, this pi bond will then go there, and this pi bond will then go there. It's a 3-arrow system for a benzene ring. They're basically just interchanging locations. That's why we often denote benzene with a circle in the middle, right? Because the pi bonds are genuinely constantly and rapidly moving within the benzene ring. But those are the major resonance patterns. We will do some more problems on them later.